Good morning, good afternoon, and good evening. I am Viral Vigela, and I'm here with our presenters, Angela Criswell and Ted Wong.
Hi, everyone.
Hello.
Today, we conclude our webinar series, Decoding Defects, Failure Analysis, by learning about functional failure analysis. As we know, functional failure can occur at any point, causing a product to fail, from minor misalignment, manufacturing defects, to mechanical stress that can push the products to its limits. We will look at some examples of functional failure and see how X-ray CT can be utilized to do some root cause analysis on them. But before we begin, a few housekeeping items. Now, as usual, this is going to be an interactive live webinar. We ask that you submit your questions via the Q&A button on your screen. We'll also have some time allotted at the end of the session for a Q&A session. And any unanswered questions remaining after that will be directly responded to via email. I'll also be sharing some relevant links from Angela's presentation in the chat window, but outside of that, we will not be monitoring any raised hand or chat function in this webinar. If there's any difficulty viewing the webinar live, it is being recorded and a recording will be available beginning tomorrow. With that said, let's go ahead and get started, Angela.
Thanks, Viral, and thank you everyone for joining us today. So this is the third and final webinar in our failure analysis webinar series. We started with an introduction to failure analysis and some of the techniques that are used, including X-ray CT. And last month, Ted talked about structural failure and mechanisms for fracture. And this month, we're going to talk about functional failure. And fundamentally, functional failure happens when there's a structural and or a chemical change that ultimately causes a material or a product to fail to perform in the way that we expect it to. And not all materials and products fail in the same way, and not all failures can be investigated by using X-ray CT. So we'll talk about situations and examples where X-ray CT applies. So let's get started for today. But before that, we'd like to take a brief pause and ask all of you a question.
All right, thank you, Angela. So I'll take over for the poll question session. So to start off this webinar, we would like to ask you a question. That question is, what industry are you in? It's a multiple choice option, so you can be involved in many fields. First of them is electronics. The second is battery, and then polymer or composite CFRP, filtration, life sciences, pharmaceutical, so many. And so obviously there's a last option called the other. So we cannot cover all the fields out there, but failure is such a prevalent issue that everyone will face at some point. So we're interested to know, where are you from? So let's let the audience vote for a few moments.
Yeah, looks like most of the people have responded by now.
Mm-hmm. Okay, so then let me finish the poll and show you the result in a couple of seconds. So here is the results. So we seems like have a quite evenly distributed audience from all different fields, which is good because we'll be covering different types of failures that might be interesting to you. So with that, back to you, Angela.
Okay, thanks so much, Ted. All right, so today we are broadcasting live from the Texas coastal region. Our office is in the Woodlands, Texas, just outside of Houston, north of Houston specifically. And just to give you an idea of what we're experiencing down here in Texas, just like the rest of the country, it's pretty warm. This is the forecast from last Friday. So if you're in this area or in the South, you probably are looking for a nice, cooler place to spend your weekend or next week. And in our case, that often will take the form of maybe you look for your backyard pool or your neighborhood pool, and you'll often find families utilizing them during this hot time. However, the catch is that you need this specific life support system if you're going to be able to take advantage of that pool system. So for example, this pool life support system has filters. So it's taking the particulates out of the water as it's being circulated by these labeled green pumps. So there's a pump for the circulator on the left, and then on the right side, there's one for a cleaner to push it around and suck up things from the bottom. And of course, you have all of its accessory pipes that are connecting these things together. And then finally, you have a brain, a computer with some electrical components, maybe a remote that's telling what time things should happen. And all of these really have to work very well in combination, because if one of them fails, then that's going to ruin your weekend or vacation, because your pool might look like this. So this is a good example of a functional failure in our territory this summer that you definitely don't want to see. And it turns out that many of the components in this pool life support system are accessible for either postmortem failure analysis by CT, or perhaps in the design phase whenever you want to understand how these particular products may diminish in function over time. So that's what we're going to be talking about today. And specifically, what we're going to learn is, what is functional failure? What are the considerations when you're using X-ray CT to study it? What information can we extract from that X-ray CT data that we're collecting? And then, of course, as always, we'll look at some functional failure examples. So let's get started with asking the question, what exactly is a functional failure? Well, the simplest example here I can show is a light bulb. And in this case, it's basically a switch. There's a filament inside, and if you turn off the switch, or unfortunately if the filament breaks, then you have no light and you have a complete loss of function. But most products don't work in that way. Instead, you have, for example, this flow of liquid maybe throughout your pool circulation, and over time, that flow may be choked down to a very slow rate. And in that case, you have diminished function. And I would argue that diminished function is as important, if not more important, to understand than complete loss of function, because that's going to help us in all phases of the product lifetime. So how can we access information about loss or diminished function using X-ray CT? What can we investigate? So, well, it really turns out it's a question of scale in the case of X-ray CT. And what do I mean by that? I mean, for example, this chart here. So this is sort of the resolution ranges that are accessible by a variety of X-ray CT systems, from clinical to industrial, micro CT, and nano CT. And if we go back and consider our pool life support system, we have the large filter. So this captures the debris in the water, and a complete filter has a length scale on the order of millimeters to many centimeters. Some of these can be quite big. Maybe a commercial system could have something as large, almost a meter in size. And so you definitely can look at these with X-ray CT, look at the assemblies, make sure there are no leaks, because if there is, then that's going to cause a problem. You may also be interested in looking at the filter component inside rather than complete assembly. Maybe you want to examine the pleat structure, the size of the pleats, the angles in the pleats, and so on. And if maybe post-mortem to look at if debris is distributed throughout, or if it's favored for one area over the other. Or perhaps you're even interested in a smaller scale, looking at the filter media itself and how that structure changes over its lifetime. So that's also accessible by micro CT instruments, but these fibers can be quite small. And in that case, you can use a micro CT instrument, but they may push into the area where you need submicron resolution capabilities, and you're going to have to use things like X-ray microscopy or nano CT to resolve them. And that's certainly true in the case of fuel filters, where they're hollow fibers and the shell of the fiber can be quite small. So depending on the length scale of what you're looking at, then you might choose a completely different instrument. You're also going to have to consider the energy at which you're going to use. And all of those instruments will range in the energies they provide and the size of the systems that they provide. And if you've been to previous webinars, this particular plot will look familiar to you. So this is the X-ray energy versus the resolution. And the general trend when choosing an instrument is if you have a very large, high density, heavy material, then you want to use high energy, and your features inside are probably on the larger side. So you definitely don't need high resolution capabilities. So if you're looking at your entire pool pump assembly, high energy, low resolution is probably fine, industrial CT. If instead you're moving to the filter module itself, the batteries that are in the remote or electrical components, then perhaps you still need somewhat high energy in some cases, and you're going to need a little bit higher resolution in that case. And then as you push into the scale of looking at, say, small fibers or filter media, microelectronics in various parts, maybe you want to examine the O-rings themselves and whether or not there's porosity there. You're going to need low energy, but you're also going to need high resolution capabilities. So all of these will factor into your choice. And if you're interested in understanding more how you make those choices, I would recommend that you watch some of our earlier webinars. We have a complete series focused on different product types and how you might approach them for data collection. But the big scheme of things is that you need to collect some CT data for your components, and it differs depending on what it's made of and how big it is. So after you've collected your data, what's next for failure analysis? Well, it turns out sometimes 3D inspection is absolutely enough. That's all you need. But in other cases, you may require quantitative analyses. And in that case, you're going to have to perform some sort of segmentation of the data into the different phases or parts. And then after you've done quantitative analyses, that may not be sufficient as well. So you can leverage some programs and their ability to do simulations so that you can either optimize design or look how this product performs throughout its life cycle, so that they can be quite powerful. So we're going to kind of go through this process together with some more details. So let's take a simple example, simple inspection. So this is a really simple example. This is an LED. There are plenty of those in your pool and in your controls, and they require a continuous circuit. So in this case, you can clearly see that there's a wire broken. And if you were imaging an LED and zoomed in on this area, you could clearly say, that's why it failed most likely. There may be problems elsewhere, but that's definitely a failure point. Though other electrical components can be more complex, however. So in this case, this is a sample that obviously has several boards. It's inside of a plastic housing that's now been made transparent. There are many screws. There's a camera actually inside of this. There are many solders on the soldering board, capacitors, all sorts of different components. So simple inspection is probably enough to confirm that the components are there, or probably to do some other visual inspection. And if you need to dive in a little deeper, you also have 2D capabilities to interrogate your 3D data. So for example, you might be looking for breaks in the wiring or other components. And generally, every vendor of X-ray CT equipment is going to have some tool that allows you to have a look at it in 2D and see what's going on inside. And in this case, it's just a short video showing someone zooming in and having a look at solders that are present in a certain area of one of the boards. And there's a lot of voids, but you can see that there is complete wetting, so there's a continuous circuit, so this part works. However, sometimes simple inspections like this are not sufficient. And in that case, we have to take a step further. And that's generally where segmentation becomes involved. And so we're going to go talk about that. Before we do, we have another question for you, the audience.
All right, thank you, Angela. So I'll take over for the poll question session again. Today's poll question, the number 2 poll question is, which experimental techniques do you currently use? Again, this is a multiple choice question because dealing with tricky failure analysis, you likely would use more than one tool. And the first tool option is optical microscopy. Second one is SEM, scanning electron microscopy. The third one is X-ray CT. Fourth one, scanning acoustic microscopy. And as usual, some other techniques that we didn't list on all top of these options. So let's let the audience answer them for a couple more moments. Oh, so it looks like a lot of people are already using CT, and that which is good. Yeah, I mean, it is natural. It's a very powerful 3D tool. I mean, so okay, so let me end the poll in a couple of seconds and show you the results. So here is the results from our audience. And back to you, Angela.
Oh, well, it's great to see a lot of people using X-ray CT, and I'm not surprised by optical and SEM. Very key techniques for sure.
Lots of microscopy.
Lots of microscopy. So yeah, and good to see some scanning acoustic as well. So let's go on and let's talk a little bit about what happens when simple inspection isn't enough in that case. So like I said, you're going to have to perform some sort of segmentation, and the difficulty of that depends on what you're looking at, of course. So let's go back to our simplest example in this case. So here we see that in this image of the LED, we have some very dark areas, some medium gray areas that are part of the LED, and the very bright wiring for the LED. And if we have a look at the histogram in this case, then we see two distinct peaks, one of which is corresponding to the voxels that are darkest, or the air in the scan, and the others that are corresponding to the LED. And there's a single peak because both the medium intensity and bright intensity all occur within the same area. So as you can imagine, this can be quite easy to segment. You have very good quality and contrast, so we can just select this single peak from our histogram of data and let's say, okay, I'm going to assign this as the LED portions. And then I'm going to say the other things are air. And now I have segmented data in this case. So now you can go on and ask quantitative questions if you want to. You could even probably easily crop out this area where the wiring is and ask some questions about it quite easily. So several minutes and you're ready to go. But that's not always what happens. So here's, so that last sample was collected on our benchtop CT lab HSEC system. And this is a foam material that was collected on our Nano 3DX. And here you can see it's similar. It's two-phase. There's the air component and there's a polymer component. But if we look at the histogram of this, it's a single peak. So the air in the polymer overlap, and probably this long tail is the polymer. And simply picking a region in the histogram will not sufficiently segment this data, because if you try, you'll see that, okay, some of the polymer is not fully labeled, and then some of the air is mislabeled as polymer. So you have to do something else to segment this. And in that case, that's where artificial intelligence can help. So when you do that, you have two different tools you can use. You can use machine learning or deep learning, and depending on the actual software product you're using, they'll offer one or the other or both. In that case, what you generally do is you just paint a couple of regions. So you can label some air as blue, you can label some polymer as yellow, and you also will benefit if you give it some context of what different phases are touching one another and their location in the image. So you want to paint some of those regions too, but it should be really quick to do. Then you plug it into a tool where either machine learning or deep learning, your ground truth is used to train, and then you creates a model for you, and then use that model to then assign the phase for the entire three-dimensional image. And this can either be very fast or it can take a while. So anywhere from, say, an hour to days, depending on the complexity of the image you have. And of course, it's quite easy with this polymer air example. Now that you have it all extracted, you can very quickly just click on the polymer and it'll tell you what volume fraction is associated with the polymer. So then you can quickly investigate some quantitative features. And the things that are accessible, of course, are the volume fraction analysis that we just talked about. And once you have the airspace identified, then porosity itself is something that's very interesting to study. Remember, if you attended last month, Ted talked about porosity or small pores inside and how those increase the stress, the mechanical stress, and can lead to fracture. And of course, its location, whether it's open or versus closed porosity, will impact the stresses that you have. And of course, these small pores can propagate into cracks that eventually cause structural failure. Also, we looked at wiring, so you might want to look at continuity or discontinuity and take advantage of some of the morphological tools that exist in these programs to extract information. And orientation is something that always becomes important with CT data analysis. Either how are things aligned, are they touching, and are there voids in between? So once we have the data segmented, then we can go on to the next phase of analysis. So I want to go on to look at some examples, but first I want to just briefly stop and see if we have any questions.
Yeah, we could. You mentioned the machine learning and deep learning, Angela, and a couple of slides before this. Can we use both deep learning and machine learning together to optimize segmentation? And what happens when you have just a two-phase example like you showed us versus like a multiple phase example, and how difficult that can be, or time consuming, I guess.
Yeah, so it turns out that machine learning is highly grayscale biased. If you have simple 2 and 3 phases, machine learning may get you to where you need to be. However, complex cases with many phases, they're probably going to require deep learning. And the advantage that it's going to provide you is that it will take into the context of location. Let's say that where things that are touching, what their shapes are, where they're located within the scan, either at one part or one end of the part or the other. So it adds a more complexity in there. And that's why it's used so prevalently. It can identify a cat versus a dog because it inherently has tools like that.
Gotcha. I think that was the only question we had. We can move on to the examples, I guess.
Okay, so yeah, so let's take a look at some examples. So I mentioned that, it's earlier, there's no general rule for how things fail, and everything fails in a different way. And one product is maybe extremely different from another one. So there's nothing general that you can extract that say covers every single case in functional failure analysis. So let's start with showing a few examples here. So the first one that I'm going to show you is a microchannel heat exchanger. So these are things that you would find, let's say, for example, in automotive equipment, maybe your refrigerator for cooling. Basically, you might find them in some electronic components. And so in this case, what you have is a heat transfer tube where you have a refrigerant flowing through. and adjacent microchannels are connected by fins. And this picture from a 2022 publication shows the larger assembly where it shows the direction of flow for the refrigerant, and then the air goes across the fins to help to exchange heat. And we had a small section of one of these, and this is a microchannel section, and the fins themselves are cropped out. Data were collected on the CT Lab HX benchtop system, and the goal of this experiment is, well, we know that there's something wrong here and there's a leak. How can we find it? So there are some conventional tools you can use to test for leaks. Maybe you apply some coating to some areas where you suspect the leak is located, and you might see bubbling in that case. But how could we do this conceptually by X-ray CT? So this is the 3D volume we just saw, and if we take a different look at it, this is a 2D cross-section, again looking through the microchannels, and we know that there's a connection between the microchannel and the outside air. We can look at it 90 degrees relative, and one of the things you'll notice about this image is that it's a simple two-phase sample, and the data quality are very good, and you have very good contrast. So this is like our LED example where we could simply use histogram thresholding to segment. And in that case, we can pick the brightest peak to label the metal portion of this and say, okay, everything outside is also air, and it's easily segmented. So at this point, you could look at the microchannel characteristics, the thickness of the metal parts. But if what you really want to do is perhaps to get at the leak, then you can ask the question, which is the biggest individual segment that's connected to air? And that will be your leak. So in this case, what you see is this one section right here lit up that's connected to the outside air, and you can then crop every thing out and just look at it in particular. So this is the 3D volume that's mapping where the leak is located, and we can look closer now throughout the length of the microchannel to get to the leak, and again crop further to ask more specific questions. So in this case, you might be interested in, what does this look like? What is the thickness of the leak in this case? And so this is a thickness mesh that's calculated for that small portion, and you can see that it's smaller on the inside, larger on the outside, so you can infer that it's blowing out versus in. And that makes sense since there's pressure with things flowing inside, and that the general length scale for these things is ranging up to, say, 162 microns in thickness. So the thinner things are purple, then as they get thicker, they're green, and then yellow in that case. So here's a simple example of a microchannel and how we might quickly segment that data to perhaps find leaks or characterize the channels or metal itself. So how about a different example? So in this case, let's look at lithium-ion batteries. So these are a very important product globally, and compared to traditional battery technology, lithium-ion batteries offer several advantages. They recharge faster, they have higher energy density and a lighter package, they're more energy efficient, they're durable, they have a longer life cycle. All good things, great, which is why we really want to understand them and optimize them, because they're used in many of the components of our everyday life. So the laptop I'm using right now is using one of these, my cell phone, your cell phone, our hybrid and electric vehicles, they all use these. So data were collected for an 18650 battery, and it's shown here with the kind of a blue shell. And these are very commonly used, and they have the name 18650 because they have an 18 millimeter diameter and a 65 millimeter height. And if you take a look on the inside of this battery, so we just cut away to look at it. Again, it's a 3D volume that's clipped, and you see that inside the lithium-ion battery contains an anode and a cathode, and the anode overhangs the cathode by a small amount, so it makes that structure very easy to identify. So there are some other things that are in here. So for example, the casing, the upper electronics are cropped out, but you can imagine that this particular type of sample would be more difficult to segment. So you're going to have to use something more sophisticated than simple histogram thresholding. So let's talk about these batteries for just a little bit. So it turns out that the anode and cathode are separated by a polymer film, and this battery is filled with a liquid or gel electrolyte. And when you use the battery, it's discharged, it releases lithium, and those ions they can travel over to the cathode. And when that happens, there is a current that allows the product to run in that case. And so we're already charging in this case, and basically the lithium ions are going into the reverse direction, and that adds charge to the battery in the device. Well, it turns out that this discharge cycle, it is not 100% efficient, meaning that 100% of the ions don't move back and forth each time you charge and discharge. Instead, you usually end up with some lithium accumulation, and that accumulation can form stress, and it can form cracks, it can form gas inside, and with more charge and discharge cycles, the battery capacity is reduced until the battery reaches its end of life. And generally that's defined by the industry at about 80% capacity. And you've seen this. Let's say that you have a new battery and it works really well. It'll last a long time with a single charge, but 2-3 years down the line, then that's no longer the case. You can charge it and it may only last an hour. So that's effectively what's going on. Now, lithium-ion batteries can come in a variety of forms. So this is an image from a 2020 publication by Chen and colleagues, and it shows the array of those formats that are used. So there are, for example, a coin cell format. There's the cylindrical cell, like the 18650 battery that we looked at just a second ago. There are the prismatic types. These are sometimes referred to as jelly rolls. Say it's the same roll featured in the cylinder, but just a different format, like a rectangle. And then there are also pouch cells in this case. So they're more flat. And the battery format will depend on the application the battery is used for, as well as the storage format. And usually those individual batteries are then assembled into multiple battery packs, and they incorporate some circuitry to protect against overcharge or discharge. And so you can see that the complexity of the sample can increase quite a bit, which makes it more and more challenging for X-ray CT data collection as well as X-ray CT segmentation. So I hinted a little bit about things that can go wrong. What else can go, what are things that go wrong in batteries, and what might we see in an X-ray CT scan? So let's have a look at, this is a lithium-ion battery from a digital camera. So here's a photograph of the battery on the left, and on the right is a 3D volume. This particular battery was scanned using the CT Lab HX instrument, and here's just a short video of that. So here you can see the outside casing. We can adjust the histogram and so that we can take a look inside to see what the internal structure looks like. And what we see in that case are, now we can see some of the electrical components. We can see the jelly roll, and you can see some sort of layering and an internal metal part that's inside. One of the things that battery manufacturers are generally doing is that they're looking at this layering and the anode overhang, and many programs have they can characterize the properties of the anode overhang to see if it's bent, if it's curled, and so on. One more advance. But there are some other things that could also be important that you can see in this case. So if we take a cut straight through vertically, so this is a 2D cross section, and we can see these layering. And like I said, this is an important part to characterize. You can also see there's some heavy metal things. This is the inside of the roll. And this would be quite complicated to segment. So I'm gonna show you how we did that. So this is a good battery. What does a bad battery look like? Here's the good battery, and here's the bad battery. So a battery that was known to have diminished function was also scanned with the CT Lab HX instrument. And it's not the exact same battery or maybe the same brand, but generally the characteristics are the same when you compare them. So you have these upper electronics and you have the layered structure inside. But however, on the left, the good battery has a nice uniform intensity throughout. But for the bad battery, there is this darkened section in the middle. So this is starting to perhaps point you in the direction of maybe a problem area inside. So if we again take that vertical cut through, remember the good battery, you can nicely see the layers and other components inside. For the bad battery, there's something more complicated going on. So you definitely see the layering, but now you see some of the layers are showing up in the middle as well. And if we look at a 2D cross section 90 degrees relative to that, then you can kind of see why that happens. So the good battery has very uniform thickness for the layers, but for the bad battery, you see some expansion and the layers are no longer uniformly spaced. So that's why you're starting to pick them up when we take the slice through the middle. If we look at a top-down view cross-section, it becomes even more apparent how this change or deformation happens across the battery. So the top is the good battery in this case, and the bottom is the bad, and we see that there's something happening throughout. And remember, I said that you get lithium accumulation, and that can cause stress. The layers, they start to delaminate, and you get these pockets or voids, and that's essentially what's happening in this case. And you can usually detect that by external view, because you'll look at a battery you might take out of your device and it may look swollen. Well, essentially, this is the type of thing that may be going on inside of those swollen batteries. So one of the things that we were interested in doing is looking at and characterizing the shape of this delamination inside the battery. And in this case, deep learning was used. So a small couple of slices were painted for the different sections, and we cropped into a small area to eliminate any of the casing or electronics to simplify the analysis in this case. So a ground truth was labeled. It was used to teach a deep learning model, and then that deep learning model was used to segment this small section, and we end up with the result that we see here. And so now we have the layers that are labeled in this case, this area of deformity inside, it's a little bit of the casing. So we can look at the thickness of perhaps those layers, but in this case, I mentioned that we were more interested in this delaminated area. So this is a thickness mesh that shows the variation in thickness of this deformation inside, from something that's very thin, about 40 microns thick, to something that gets larger and wider as you go towards the outside edges of the battery, where it's like 5 times larger in that case. So this is something that we can easily do using X-ray TT. But like I mentioned, not all batteries come in the same format. And also, we may be more interested in things on a different scale. Maybe we want to take an even deeper dive in this case. So our next example is going to look at this. In this case, this is our last example. This particular data set was collected using our Nano 3DX instrument, and it was chosen because it's capable of submicron resolution CT data collection. And these particular researchers from the Osaka Prefecture University wanted to examine how solid-state lithium metal batteries begin to fail. So they created a setup on their instrument so that they could collect data in real time and look to see what's happening. So this example right here is showing you projection images over time of a specific area. And the projection images really aren't telling you very much. So instead, the researchers took it a step further and said, let's do in situ data collection. So in situ data were collected at various time points, and those are highlighted by these sections 1, 2, 3, 4, 5, and 6. And in the CT data following reconstruction, they said, well, let's look at different areas of the battery. So for example, this yellow highlighted area where there's the lithium LPS layer, and then inside the LPS layer, this orange dotted area. So this shows 2D cross sections from those areas where you see the gradual buildup of some small cracks that eventually develop into larger cracks over time. So the next step they wanted to do is to do some ex situ scans, and I thought it was interesting their setup. So here's a small video that they provided in the supplemental information from their paper. If you're interested in that, there's a link that Viral's going to include. So yeah, you can ask lots of questions. I certainly think it's fascinating and interesting setup. So in this case, they are using a moly source. The field of view is 2.6 millimeters, and the voxel size is 2.5 microns. So again, it's collecting data with the attached apparatus that they're using for charging and discharging, and you can see some of the cracks in this case for some of the projections. Following reconstruction, they produced this 3-dimensional video here of the crack and shows how it propagates. So, and they took this data along with data from XRD to characterize different areas and SEM to understand what exactly was happening structurally inside. And in this paper, they explained that there are chemical changes identified by XRD within the battery that led to lithium cluster formation. And those clusters caused concentrated stress and ultimately the formation of our cracks. And over time, the cracks cause short circuiting of the battery and eventually a failure. So this is a good example of how chemical changes ultimately cause fracture or structural change that leads to diminished function and ultimately loss of function. So work by this group and others doing similar things with CT, they help us understand how batteries fail, their failure processes, and will help us make better batteries for the future. So I did hint at the beginning that sometimes simulations can help. So we've looked at a real life example. How about examples with simulation? But before we go that, I just want to stop and see if there are any questions.
We do have a couple of questions. I think let's go back to the slide when you talked about machine learning and deep learning, Angela. There is a question from there.
Okay.
And it says, is there an advantage to deep learning for segmentation if I have a lot of data but haven't yet trained the system to classify the different segments? And to add to that, in order to do segmentation, I need to perform machine learning anyway, so adding data doesn't help. How in such case is there an advantage to deep learning versus machine learning?
So in those, I think I'm just having a look at the question, so I make sure. So is there an advantage to deep learning for segmentation if I have a lot of data but haven't trained the system to classify? Yes and no. So for example, there are groups that are asking the question that what if I just take lots and lots of CT data that's been labeled by others and throw it into one large deep learning ground truth and create a model? Will it work for a broad range of samples? And it turns out that is the case, and there is something, a tool like that in Dragonfly. But generally, you definitely want to train some of your own data to supplement in that case. So there's definitely an advantage, and you should take some of your CT data, label it to contribute to the ground truth, or just use your own labeled data as a ground truth. I hope I understood that question correctly. Got that?
We can also take it offline and
Yeah,
discuss it via email or another meeting.
yeah.
But
And if there are specific things for sure, I'd love to talk to you or chat with you about that.
yeah. And then just a brief question about thickness and gaps in battery, how important it is. And, we talked about lithium getting stuck. How challenging is that on a typical battery, and how often does that kind of happen? I guess is what we're asking here.
Gotcha. So it turns out that it's the accumulation of lithium and the creation of voids is a fundamental failure technique. Remember, I told you there's electrolyte inside, and the lithium ions require a continuous path of electrolyte in order to flow from the anode to the cathode and vice versa. If that's disrupted by some air pocket, then lithium cannot flow, and it essentially becomes trapped unless there's another mechanism or direction of flow. So once that starts happening, then it's only a matter of time for your battery. So those pockets or areas of delamination are very important to understand.
Then you get those clusters and structural failures.
That's
Yeah,
where they
yeah,
start.
yeah.
So the results of this group, they identified, yeah, these are certainly lithium clusters. That's where things start to go wrong.
Yeah, we also do XRD, by the way.
Yes. Yeah.
I think that's it. We can move on to the simulation portion.
Okay,
Yeah.
sounds good. So let's go to the next slide. So like I said, we looked at examples of CT using in situ or ex situ experiments, but I also mentioned that we can leverage simulation to help in our understanding of functional failure. Exactly how does that work? So, well, there's a lot of third-party programs that are capable of importing CT data and or say CAD drawings. And from those, you can extract the functional data from the 3D volume itself, or you can perform these simulations. And one example is that is what Ted showed you last month. So he did some mechanical simulations from CT data of an additively manufactured sample. Those were done with VG Studio Max, a program from Hexagon, to show stress points or concentrations of stress that can point you of like, this are the regions that are most likely to fail. That software also has some tools for fixture simulations. And by that, I mean, you can you can collect data for a deformed part and ask whether the part will still be in tolerance once you put it virtually into the assembly. So you import your CAD, get your deformed part, you dock it in or assemble it virtually, and ask the question similar to mechanical stuff: what's the deformation, and are we still in tolerance or out of tolerance? And is this part, this whole assembly likely to work? Poor analysis network modeling is extremely important for a variety of different types of products, and those are covered in most of the third-party packages. So VG Studio has simulations for this. Dragonfly has simulations for this. And of course, batteries are fundamental for how we live our everyday life, and they're very accessible with programs like GeoDict and VG Studio Max. So you can perform quantitative simulation of battery aging, lithium migration, and look at things at a microstructural level to understand them. And one last example that I'll mention are simulations where you can look at the flow of liquids. For example, you can do flow experiments with air, with water, with oil, and others through a material or filter. Maybe you want to know how things flow through rocks if you're a geologist or in the oil and gas industry. And or maybe you're looking at filter design and you want to understand how that process works in finer detail. So for the last example today, what I'd like to do is to show you a filtration simulation example. So in this case, I'm extracting some of this from a broader webinar series that we did previously, where it's a deep dive into episode 1, collecting CT data for filters, episode 2, analysis of those filters, and episode 3, simulating. So if you want to know in nitty-gritty detail how to do this with Geodict, watch that, because we go step by step by step. So let's go back and to the beginning of this webinar and recall that I talked about different scales at which we can look at the filtration process for our pool to understand it and make better filters. So in this case, for the last step of this, we're going to look at some filter media and simulate some flow experiments with Geodict. So in that earlier webinar series, I described how to perform filtration simulation experiments. And in that case, the Geodict program flows a fluid containing particles of user-defined sizes in a distribution through the filter media to extract some quantitative measures and properties for the filter media. And the important properties we talked about for filters are, first, the pressure drop. So this describes the pressure increase with the loading of the filter. And it's basically the pressure differential between the top and the bottom of the filter. Another important property that we learned about was the dust holding capacity. So you get a measure of the total capacity of the filter, and that's correlated to the total volume of trapped particles. So you can directly calculate that from the simulations. And thirdly, you get a measure of the filter efficiency, which reflects how well that filter traps those particles of different sizes. So the efficiency is by particle size and overall. Geodict also has capability for simulating filter lifetime. And in that case, you're simply going to run experiments until you've totally clogged it or reach some maximum pressure drop. So here on the left is a 3D volume of filter data that were collected with the Nano 3DX system. It's just a small portion of the filter, of course. And on the right side is a 2D cross-section where we see the individual fiber cross-sections, as well as these light gray areas in here that extend horizontally. And these are areas where binder is located. So the stuff that's holding all the fibers together into a cohesive package. So you can import CT data into Geodict, and it has segmentation tools to label the filter media material. And in this case, the data quality and contrast for that scan I just showed you are sufficiently high that we can use simple window leveling for segmentation. The software also has image processing and artificial intelligence segmentation tools for those cases where you might have data that aren't so good, not as good. And what you end up with is the segmented media volume that's shown here in 3D on the left. So that's what that would look like. And then Geodict AI tools, they analyze this segmented data volume to identify individual fibers from which fiber properties and distributions can be calculated, including the fiber diameters and lengths and the fiber size distribution across the filter depth. So here you see that the mean fiber diameter changes from smaller to larger with increasing depth through the filter. And additionally, Geodict has AI tools to identify binder within the segmented volume as well. So once you have all of your filter media characterized, then you can either do simulations, but you can also create virtual media or variations on your a given fiber, and then also perform simulations with them. So what does that look like? So once the filter media are segmented, you perform the simulation, and here's the result of a flow dict simulation. So you're simulating a flow of particles that start at some boundary, and then they go through the filter media. Some are captured, and then others go all the way through the filter until they reach another boundary in that case. So you get particle trajectories, you get trapped particles, and other information. For example, you can look at the trajectories or flow throughout, the pressure throughout. And in this case, we see on the right, this red color is associated with the velocity of the particles. So some are moving very fast, some are moving slower. And in those areas where binder is, you might intuitively expect that flow would be slower than it would be in other areas. So you can characterize this in a number of different ways. So, but what you probably notice is that from this experiment, we don't really see that the simulation represents the total dust holding capacity of the filter. However, if we run the simulation many, many times, either till we can set a maximum pressure drop or a maximum time, we get the filter lifetime, and we get the total pressure drop and the dust holding capacity of that thing. So this is your filter. You can perform the same thing with your virtual filters. And in that case, you create a table or a database of information. And remember that so one of the characteristics of an ideal filter is it has low pressure drop, but high dust holding capacity. And using that criteria, you can select, oh, this is actually the best one. And then you might choose a subset of those to manufacture and then perform real world experiments and compare those to your simulations. It greatly minimizes the number of variables you have to take into account when making actual filters. So simulation in this case is very useful for designing filters, and it helps us understand how filters diminish in function over time, and perhaps keep our pools clean for the summer so we can enjoy that nice, refreshing swim. So with that generally, we're going to wrap things up today. And what we just learned, we looked at functional failure in the context of loss of function as well as diminished function. We looked at some considerations when we want to use X-ray CT to examine our functional failure. And we looked at the types of information, quantitative and otherwise, that we can extract. And finally, we wrapped up by looking at some examples and specifically described how you might also leverage simulation to help in your understanding of functional failure. So I hope you found some useful information today. I really want to thank you very much for joining us and hope that you enjoy your summer ahead. With that, we have time for some questions.
I don't see any questions at the moment, but if any questions do come up, we'll kind of reach out to them directly via email. I think I just shared some link on our upcoming webinar. This concludes our Decoding Defects Failure Analysis webinar series. We will be back in a couple of months on August 21st at 1 p.m. Central Time. We'll talk about non-destructive inspection of batteries using X-ray CT. It's going to be part of our Beneath the Surface webinar series on battery materials, and we look forward to seeing everybody in a couple of months.
Yeah,
I also shared.
Yeah, I'll just mention with that one, it goes through a variety of X-ray techniques. So it starts with a couple of XRD, some X-ray CT, some XRF. So you get to see how you use a range of different tools.
Yeah, it's a battery industry application specific webinar that includes all of Rigaku's core technologies throughout the series. So that's in a couple of months. And then I also shared a link to our newsletter. If you haven't already subscribed, please check it out, and be sure to subscribe it to our monthly newsletter for the latest updates on vlogs, webinars, any recommended publications related to X-ray CT. It's going to be really, really great every month where you get, news and updates on what we're doing here at Rigaku. So that is all we have for today. Thank you again for joining us. We'll see you guys in a couple of months. Have a great summer.
Thank you. Thanks,
Thank
everyone.
you.